Hi guys, welcome back to my YouTube channel. So today we'll be talking about conventive mode of heat transfer. But before we move into what we have for today, if you are just stumbling on this video, please kindly hit the subscribe button. If you're a subscriber, thank you so much for subscribing. But do not forget to like, comment, share too departmental groups and people you know that this video is going to benefit. So let's get right into what we have for us. So we are talking about conventive mode of heat transfer. So we have three basic modes of heat transfer. We have the conduction, the convection, and the radiation. So if you check out my previous videos, we've talked about conduction. So now we are talking about convective mode of heat transfer, which simply implies convection. So convection is the transfer of heat from one point to another within a fluid by mixing of hot and cold portion of fluid. So basically, convection deals with a fluid. Yeah, a fluid must be involved. So it deals is the transfer of heat from one point to another within a fluid. Like I mentioned, a fluid. It's very important. It deals with fluids by mixing of hot and cold portions of fluid by mixing them together. So it uses Newton's law of cooling, and the mathematical expression is this: Q equals to HA Cs minus T no infinity. And our Q is the rate of radiative heat, which is the which is in watts rather. Our H is the coefficient of heat transfer, which is in watts per meter square Kelvin. Then our A is the surface area in meter square. Our Ts is the temperature of the surface. It can either be in degrees C or in Kelvin. And our T infinity is the temperature of the surrounding, which can be in degrees C or Kelvin too. So basically, this is the formula that I'll be using for the convective mode of it for convention. Now, thermal resistance in convention deals with R equals to 1 over HA. So therefore, if our R is 1 over HA, then our Q is the 13 over R. So these are the basic formulas that I'll be using for convention rather. I'll be using for convention. So let's get right into our first question. A vertical pipe with a diameter 0.1 meter is carrying hot water at a temperature of 90 degrees C. The surrounding air at a temperature of 25 degrees C. The pipe is surrounded by air with a convective heat transfer coefficient of 25 watts meter square Kelvin. The length of the pipe is 5 meter. Calculate 1. The heat transfer rate. 2. The heat flux. 3. The heat transfer per unit length. And 4. The thermal resistance due to convention. And they said our R is 0.05. So as always, let's write out our parameters. So it said the diameter is 0.1 meter. The carrying hot water at a temperature of T1 90 degrees C. We don't need to change it to Kelvin since it can either be 90 degrees C or Kelvin. So the T2 now, or let's say Ts, that's the surface, and the T surrounding is surrounded with a surrounding air has a temperature of 25 degrees C. The pipe is surrounded by air with a convective heat transfer coefficient of 25 watts per meter square Kelvin. Then the length of the pipe is 5 meter. So we have to calculate Q, heat flux. So for units per area, we can denote it as this, which is heat flux. Our heat flux is our units per area, rate per area rather. Then the heat transfer per unit length, you can say just 1. Then the thermal resistance due to convention, that's our R. So these are the things that we asked to look for. So let's get right into it. So if we want to get our Q, what's the formula for Q? HACS minus T. So do we have our area? No. We can calculate it. And since they said it's a pipe, a cylindrical pipe now, so our area would be 2 pi RL. So now, since our R, okay, I didn't even write it, is 0.05. So that's 2 times 0.05 multiplied by 3.142. Then what's the length? 5. So what's our area? So our area is giving us 1.571 meter square. So we cannot calculate our Q, which should now be equals to HACS minus T of this. So our H is 25, which is our coefficient, our heat transfer coefficient. Then our A is 1.571. Then our TS is 90, and our T, this thing is 25. So what this is going to give us? So you have 2552.88 watts. So since we've gotten our Q, then now let's calculate our heat flux. I already know that heat flux is Q over A. So what's our Q? 2552.88. And what's our A? 1.57. So we can get this. So we have 1625 watts per meter square. So the next one, we have to calculate our heat transfer per unit length. And heat transfer per unit length simply means the heat per length. That's just what they're trying to tell us that we should calculate. And we denoted it as this. So that's Q over L. And what's our Q? Capital Q now. That's 2552.88. Then what's our length? 5. So what's this going to give us? So our final answer is 510.58 watts per meter. Then the last question, we have to calculate the thermal resistance due to convention. And the thermal resistance due to convention is, which is R, 1 over H. So that's 1 divided by, what's H? 25. And what's our A? 1.571. So what's this going to give us? This is 0.025 degrees centigrade. So everything we have to calculate, we've gotten them. So let's have a recap. We're given all of these parameters. We have to look for our total heat transfer rate, our heat flux, our heat per unit length, and our thermal resistance. And we look for that for convention, the Q, which is the heat transfer rate, is HA open bracket Ts minus T infinity. This Ts is the surface temperature, and this is the surrounding temperature. So our area, since what we need to calculate is capital Q. So we have our H. We do not have A. We have test. We have this. We can calculate our A since we are using a pipe. So the area for the pipe is 2 pi RL. So we calculated that. And since we've gotten our area, we can now calculate our Q. So after calculating our Q, then we move to, that's the first question. Then we move to the second question. And we have to calculate the heat flux. Normally, it would have been denoted with Q, but since we are also asked to calculate the heat transfer per unit length, that's why we use double bar to denote it. So I already know our heat flux is capital Q over A. Heat flux is heat rate per unit area, which is Q over A. So Q over A rather, and we got that. Inputted our values and we got that. Then the third one, we have to calculate the heat transfer per unit length. And we did that. That's heat transfer per unit length. That's per length. And we got that. And the last question, we have to calculate our thermal resistance, which is 1 over HA. And we did that. So let's move to overall heat transfer coefficient.